I'm going to turn a grill plate into a 3D printer, which makes sense if you think about it. They are affordable, widely available in different sizes, heat up fast
100 degrees already?
and get hot enough to grill chicken on it. However, this printer will be unlike anything else. I went to Form Next with Max from Drop Effect and this bloke, and I couldn't find anything like it. Yet this can be revolutionary. The idea is to use two of my previous ideas. The truss gantry, and if we go even further back in time, the moving portal mod. The bed stays stationary and the tool moves in all three dimensions. The portal can be tilted at an angle, which is useful when I'm going to 3D print my own shoes. Not just any shoes, proper shoes. Eventually we can add more portals and do real multi-material printing, like combining resin with normal printing or whatever combination we can come up with to find new properties. Now the long narrow shape makes sense. The heat? That's just an added bonus, and who knows if this becomes useful. I found this old grill plate in my attic, the 1800 watts Cuisine Deluxe XL Teppanyaki grill plate. And let's see how well it performs. First I want to see how hot this actually gets. And I'm curious how fast it will heat up. So let's crank it up and see for ourselves. With that knowledge, we can have a better understanding of how we are going to control it with our 3D printer controller. I can already feel the heat. Oh wow! That looks awesome on the FLIR camera. Wow! 100 degrees already in 1.5 minutes? It heats up fast. This is typical odor, you know? Okay, this thing gets hot. At what temperature shall we call it? You can hear it. Oh, there's smoke coming out. Oh, okay. Let's say that this is good enough. So if you're going to control this with a 3D printer controller, we have to set these parameters in firmware, what the absolute maximum values are. And I think that 250 is a nice number. I'm going to open this thing because I'm curious how this thermostat actually works. This thermostat are two pieces of metal, different metals, steel and copper. The knob is basically just a screw and you set a certain amount of tension and then it clicks into the other direction. And once it heats up, it will click back. So that's an interesting thing to see. Okay, this isn't particularly safe, so I wouldn't recommend doing this yourself. And now it made contact, so the circuit is closed and it heats up. And once it gets to a certain temperature, it goes off. And now the circuit is open and it cools down again. And once it has cooled down enough, then the circuit will close and then it will heat up again. But this isn't very accurate. It's also not very stable. So yeah, let's use a proper temperature controller. This is the Duet Mini 5 Plus and this is the perfect board for this project. It has everything we need, and if we need more, we can use expansion boards using CAN. When I reached out to Tony from Duet asking if they wanted to support my project, he said, "Fuck yeah, boy." Well, maybe not in that exact wording, but he was very enthusiastic. Okay, I've got several pieces of hardware. This board, a solid state relay, power supply, touchscreen controller, and I somehow have to mount everything on here. And well, I have these two FR4 boards. Yeah, I can mount stuff on here. It would be nice to have a CAD model so I don't have to just guess and start drilling in this thing. This CAD model made it a lot easier to add all the parts to it, and I started with this touchscreen. I designed a fitting enclosure for it that can be mounted to the handlebars, printed the first prototype to see how everything fits, and mounted it to the grill plate. It fits quite nicely. Then I realized that the relay has an aluminum bottom, which implies that it needs cooling. So I checked the datasheet, and sure enough, without the heatsink, the maximum possible current goes down when it gets hotter. The PCB plate is not able to conduct the heat, so I bought a sheet of aluminum. However, this sheet is wider than the PCB sheet, so I need to cut it narrower. But I don't have the right tools for that. I thought, maybe I can just make a cut using a fresh blade on both sides of the aluminum and start bending it until it breaks perfectly along that edge. If that works, let's take it a step further. This green protective layer can be burned away by the laser cutter. I added some markings and made tiny dots for the holes. I lined everything up in the software, started cutting, and things are looking good. These dots made it easy to drill the holes at the right locations. Okay, now the PCB material. This can be cut, but it cuts pretty violently. Don't expect a nice and clean cut, and this Spore X-Tool P2 55W CO2 laser cutter is turning the holes into charcoal. It can be cleaned with alcohol though, and the charred bits can be pressed out. Although I wouldn't recommend doing it like this. I drilled out the rivets from the bottom plate and clamped both the aluminum and PCB plate to it. This way I can mark where the holes need to be. Then I used the center drill, which makes drilling the larger holes easier. This is ceramic felt that can cope with high temperatures and acts as an insulator. It's easy to cut to the right size, and I placed that on the bottom plate. Next step is to add thread to this plate, and I found rivet nuts that can be placed in the holes that I drilled earlier, so we can mount aluminum and PCB plates to it. Before removing the protective film of the aluminum plate, I marked the protective earth symbol. My hope is that the laser has damaged the surface, so the marking stays on there. It looks pretty sharp. I also added the rivet nuts to this plate, and this is becoming my favorite way of adding thread to parts. Even in a PCB it works flawlessly. Before screwing in the standoffs, I added a bit of thread locker. If you have any experience with removing a motherboard from a PC, you know how annoying it is when these things come loose instead of the screw. Well, this prevents that. I drilled out the holes in the handlebars and cut thread in it so I can just mount the bottom plate with the screws instead of the rivets. I added some thick cooling paste that I found somewhere and applied that to the relay and mounted the relay to the aluminum plate. I mounted the power supply, and because we don't need much power, this thing can be pretty small, and added the zip ties for our future cable management. I mounted both sheets to the bottom plate and it's coming along nicely. Time to add the electronics. Okay, the electronics are finished. I've connected this panel dual and it looks pretty good. And lastly, I added this solder wick as a ground wire, so this aluminum grill plate itself is grounded. I use solder wick because I think that this connection gets pretty hot, so I don't have an insulator that can melt. I started off with this switch, but I replaced it with this one, not because of the nice big red button. It's because this switch has this extra pin over here that needs to be connected, otherwise it wouldn't stay on. And this switch didn't have that, so it's a lot easier. And it also fits better. Some of these components are a bit high, so I had to raise it a bit, so I made these risers. Also, if you're wondering how I'm going to print on this non-stick coating, because, well, as the name implies, the prints probably wouldn't stick, I ordered this sheet of glass at the right size, which I can just place in here, clamp it down, and just print on glass as I'm used to do. So the last thing that needs to be done is to configure the mainboard so it can heat up this build plate at the temperature that we want. I connected it to my computer, but soon realized that my grill plate doesn't have Wi-Fi. I moved it to the other room where my router is placed and connected the grill plate to the network. After configuring the network settings, the web interface loaded and I could configure the rest. Nice. It was funny to set the maximum temperature of the bed heater this high. I thought that this was going to be easy, but after many attempts the temperature sensor gave a fault and showed a pretty high temperature. Eventually my best guess was that the probe itself was broken and I found this one on Amazon. I connected that and this sensor showed the right temperature. I removed the bottom plates so it was easier to reach the right spot where the original thermostat was placed. This probe fitted pretty well there. I put everything together, turned the machine on and yeah, the heater fault was back. Turns out that when the probe comes in contact with the grounded parts, it gives a fault. So yeah, the other probe probably was just fine. But how do we solve this problem? I tried to connect the negative to ground, which got rid of the fault but gave a false reading. So the only way I could think of was to use a different probe that doesn't have the braided metal wire and add a piece of Bowden tube to it to insulate everything from ground. I pressed that in the part of the original thermostat and the fault is gone. I managed to place a sensor without disassembling everything and I'm finally ready to test. Okay, let's start with 50 degrees. Relay is on. Yes, it's heating up. Electronics work. Nice. I started the automated tuning and used a set point of 100 degrees because I expected some overshoot. Yeah. I checked if the handlebars and bottom plate were getting hot, but everything stayed nice and cold. The overshoot was quite a lot, and although I managed to tune it, the response was very slow and it looks like it's taking too long for the sensor to reach the temperature. How do we physically connect the probe closer to the heater in a reliable way without actually touching it? I tried to think of a way during this long period of tuning, and then it occurred to me. I used JB Weld in a very old video which saved the day, and I think that this is the perfect solution. It can cope with high temperatures and it fixes the probe perfectly against the heater. Once this was set, I reran the auto tuning and this time it's much better. The overshoot is less and now I'm more confident to reach higher temperatures. Oh yeah, something is happening. Yes, 220.
Hello, can you hear us? Can you hear us? Can you... Over. We are sinking. We are sinking.
Hello? This is the German Coast Guard.
We are sinking. We're sinking.
What are you thinking about?
Okay, now we are ready for the real test, but first I want to say thanks to my Patreon supporters, especially these guys, my top tier Patreon supporters. Your support helps a lot with these projects. Usually you don't think about the correct temperature for grilling meat on a plate like this, so I just set it to 190 degrees, which felt like a good starting point. This seems pretty good, so we just filled it to the brim with meat, and even under these rough circumstances it kept on going. So, is this a good idea? I would say yes. This controlled way of grilling meat went extremely well and everything was grilled to perfection. Oh wait, for using it as a base for 3D printer, this looks very promising. It already forms a decent construction to mount things to, and it's pretty easy to control. We're going to find out in the upcoming videos how well this actually performs as a 3D printer, so subscribe if you don't want to miss that.